So this is the final video for proteins and amino acids in the A-level chemistry, chapter 511 of your textbook. So we're going to look at this one about enzymes as proteins and what they actually do and how they behave. So they lower the activation energy of biological reactions. They lower it an unbelievable number of times, millions of times. They speed these reactions up. Biological or enzymes or the sort of the holy grail of catalysts, and not really anything in industrial catalysis has been able to replicate the speed at which enzymes can operate at. So they're formed by complex active sites being formed, and those complex active sites come from amino acids. Okay, within enzymes they are obviously proteins, and these primary, secondary, and tertiary structures form a very complex active site where a substrate can come and bind. They're phenomenally specific. They're actually so specific that they can tell the difference between enantiomers, between optical isomers of the same compound. Okay, so they really are phenomenal molecules. And certain enzymes only form in some cells. Okay, so you'll only find some enzymes in certain areas of the human body. And that's probably a lot of you do biology already know that. You find proteases in the stomach there to break down proteins. You find lipases, I think, off the top of my head, in sort of the bile duct and places like that to emulsify or break down fats. So how do they work? Well, there's a few different mechanisms now. The mechanism that is on the A-level spec is called the induced fit mechanism. So there are different hypotheses, different mechanisms. So if you read about them, don't worry. I'm just doing the one that you have to know about. On the induced fit, you can see here the active site of the enzyme is very different from the shape of the substrate. So we're showing that the active site of the enzyme actually changes shape. It rearranges in order to fit the substrate. Okay, and then when the substrate turns into product, okay, which we have here, you can see now the active site of the enzyme has returned to its original shape. Okay, because this is called induced fit, and this causes a reconfiguration of the shape of the amino acids and the protein that makes up the enzymes, which then goes back to what it was at the beginning. So the substrate interacts with the amino acids in the active, in the active site there, changing the secondary and tertiary structure of that active site. This allows that substrate then to fit exactly into the active site. So it's phenomenally specific, and it changes until that substrate fits perfectly. Okay, this interaction changes the structure of both the reactants and the products. Okay, the reactants and the active site, both of them change in terms of their structure, and in turn all of that rearranging and changing of those structures causes a reaction to happen at a much lower activation energy than it would have otherwise have happened at. Okay, so that's how enzymes work. That's as much as you really need to know about the induced fit hypothesis, but again, make sure you read your textbook and make sure you do learn it. So we take advantage of this in biological washing powders. We use enzymes in biological washing powders. Okay, and they contain proteases, which break down proteins, lipases, okay, which break down fats. And you can imagine you get lots of protein stains on clothes, you get fat and grease stains on clothes. So these biological enzymes that are in these washing powders are brilliant at breaking these down, and they use exactly the process that we talked about on the previous slide. And when they break them down, they turn them into water-soluble substances, and the beauty is they can now be washed away in your wash machine. So biological detergents are effective at much lower temperatures, and you can imagine they are enzymes, so they operate at roughly 37 degrees Celsius. So in actual fact, if you put them into a high temperature wash, they won't work. So they're brilliant at saving money, because they allow families across Britain to run washes to clean their clothes at much lower temperatures than you might normally do. And they're also saving fossil fuels, being more environmentally friendly, all of those things. So they're actually, as I said, they're ineffective at high temperatures. You need them to run at low temperatures. So not only do they save money, but they clean your clothes at much lower temperatures. That also means that they are much friendlier to delicate fabrics like silks and wools and stuff like that, which you really don't want to be washing at high temperatures. Okay, so that's just an example of one. Right, denaturing of enzymes. I spoke about this in the second, I think it was the second video, where you can different pHs or changing the pH of an environment for an enzyme will change and play around with particular functional groups. And when you play around and break down particular functional groups like carboxylic acids, if I had that in a pH below or above 7, well, that will turn into that. And all of these things, these changes in pH, will play around with these R groups and change the structure of amino acids, and therefore change the structure of the protein, and therefore impact upon the effectiveness of the enzyme. Okay, so you will destroy tertiary structures. And this is why people feel ill many times, because their enzymes are being impacted upon by changes in temperature and changes in pH within the human body. Different enzymes operate at different optimum pHs. So everybody thinks enzymes operate perfectly at pH 7. That's not true. Pepsin, for example, which breaks down protein in the stomach and exists in hydrochloric acid, has developed that it actually works at about a pH of about 1.5. So it's not different parts of the human body operate under different pHs, and the enzymes within those environments, okay, have adapted to those particular pHs. And you can see there, okay, this is just a graph for an enzyme that operates at about pH 8, optimum pH, pH 8. If this was for a protease, you would have its optimal activity way down here at pH 1.5. Okay, so it all depends on the enzyme and whereabouts in the body it is found. Temperature, similar sort of thing. Okay, if the chemical potential energy increases great enough, you start to weaken the bonds that make up that tertiary structure, that 3D structure of the active site of the protein of the enzyme. And once you start to break that down, then that protein can no longer do what it's meant to do. Okay, it slows down. It doesn't break down the lipase, or they break down the fats or the proteins, or carry out whatever particular job in the human body it's meant to do, and then you start to feel unwell. Okay, now enzymes do operate at their optimum at 37 degrees Celsius. So all enzymes operate at the internal body temperature of humans. Okay, or all human-based enzymes anyway. Okay. So there's our last set of questions, 511G. Okay, again, pause the video, have a go at it. Please make sure that you're marking these, boys. And that is the end of it. Okay, so that's the end of proteins and amino acids. All done. Please make sure you mark your questions, check your answers, and come and see me about things that you don't understand. Okay.